Okay, so today we are going to learn about Otto cycle. What is Otto cycle? Otto cycle is nothing but an air standard engine, okay, or air standard cycle. Because the medium which travels in throughout the cycle is going to be an air medium, okay. And Otto cycle is what? Otto cycle is nothing but an engine which runs on petrol, okay. So another name of that engine is going to be Otto cycle, and this is a type of internal combustion engine, because whatever the combustion is there, it happens within the cylinder, okay. So to make you understand Otto cycle, we are going to explain the PV diagram and what are the different points on PV diagram we are going to understand through this diagram, okay. Now to understand this diagram, or before understanding this diagram, there are some basic things about a cylinder, okay, which we need to understand. Now once we get the information about the cylinder, we are going to easily understand these diagrams and what are the corresponding points of PV diagram going to get represented in terms of these diagrams, okay. So first of all, ignore all other diagrams and concentrate on only on this diagram, okay. So first of all, there is a cylinder, okay, and in that cylinder there is a piston, okay, and then the piston is connected with a crankshaft and connecting rod, okay. Crank and connecting rod it is connected with, okay. So this is the crank, okay. When the crank rotates, what happens? When the crank rotates, when this point, this is the point, okay, this is going to rotate, this line is continuously going to rotate. When this point comes to here, okay, when this point is here, what happens? The piston will be coming down, okay. And when this point is going to be here, then piston will be at maximum height, okay. That means what? When this is going to rotate, this is going to reciprocate, okay. That means this is a mechanism in which a rotary motion is converted into a reciprocating motion. With the rotation of this crank, the piston is going to reciprocate, okay, within the cylinder. Now this is the piston, okay, and this is the maximum height where it can get, okay, where it can get. Why? Because there is some clearance volume. That clearance volume is given. Why? Because if clearance volume is not given, okay, that means the stoppers are given here, so that the piston cannot move up to the maximum height, up to here. Because if this happens, the piston head is going to hit the cylinder head, okay. This piston cylinder is going to, the piston is going to hit the cylinder head. So for safety purpose, we are giving some space, okay, so that the piston doesn't hit the cylinder head, okay. Now there is some volume, okay, there is some clearance volume, for what? It cannot reach up to the cylinder head, okay. Now let us consider that these are the, in the void space, okay, in that void space, these blue dots are the air, okay. Before the beginning of the cycle, there is some air, okay. And the diameter of the cylinder, the diameter of the cylinder is what? The diameter of the cylinder is known as bore, okay. In that cylinder, the diameter is known as bore, and this is going to be your stroke length. This is going to be stroke length. Stroke length is what? Stroke length is the length through which the piston travels, okay. Stroke length is the length through which the piston travels, okay. This is known as the stroke length. And the volume up to where this piston cannot move, or the volume which is provided for safety, is known as clearance volume. And the volume which the piston covers while reaching from top dead center to bottom dead center, or bottom dead center to top dead center, where whatever the volume that piston covers, okay, this piston is going to cover at the volume of a cylinder, okay, whose height is going to be length L, okay, whose height is going to be length L, and diameter is going to be equal to the bore. This is the amount of volume which the piston covers from while reaching from TDC to BDC, okay. That volume which that piston covers while reciprocating is going to be named as our swept volume. It is denoted by Vs. Clearance volume is denoted by Vc. This volume is denoted by Vs, okay. And let us suppose the blue dots are going to be the air. Initially, before the starting of the cycle, these are going to be some air, because in the clearance volume it is not said that it is going to vacuum, okay. So we are going to say that there are some previously installed air. Okay, and this is going to be an inlet valve and this is going to be an outlet valve. Okay, this is inlet valve means what? This while this piston comes down, a suction is produced inside the cylinder. Okay, this is the air. Okay, this is going to be the air. When the piston comes down, this air is going to expand. Okay, this air is going to expand means what? The pressure is going to come down. Okay, at some point while coming down, the pressure becomes negative, and negative pressure is what? Negative pressure is nothing but vacuum. Okay, so while coming down, it produces vacuum inside the cylinder, and when the vacuum pressure is created inside the cylinder, okay, that pressure is negatively so high. That means the vacuum pressure is so high that whatever the spring which is connecting this inlet valve opens. Okay, this inlet valve opens due to the extremely high vacuum inside the cylinder, and while the valve is opening, the air and fuel mixture comes into the cylinder. The air and fuel mixture comes into the cylinder. Okay, now these valves are what? These valves are connected with springs. Okay, now whatever the pressure is there, whatever the pressure is inside the cylinder, okay, if that is so powerful, if that pressure is so powerful, or the force due to that pressure, okay, if there is a pressure, okay, then there is some force, obviously, because force is equal to pressure into area. Okay, so when the force, okay, force that is developed due to the pressure inside the cylinder is so much high that it can overcome the spring force of that inlet valve, then this valve opens. Okay, then this valve opens, and while the valve is open, then air fuel mixture comes into the cylinder. Okay, and inside that combustion takes place, and after that exhaust takes place. When the pressure is so much high inside the cylinder during exhaust, that the spring force of this valve, spring force of this valve is going to fail with respect to, or in comparison to, the pressure inside the cylinder, and then this valve opens, the exhaust comes out through this valve. Okay, so these are the basic things of a cylinder and how it is going to act. Okay, now this is the mechanism of a cylinder I am saying. So now these are the things which are not important in terms of Otto cycle. Okay, these are the terms that is not going to be important. Okay, the main important thing is what is the position of piston, okay, inside the cylinder. Okay, this is going to be the main concern. Okay, so this is the bore, this is the length, this is clearance volume, and this is swept volume. Okay, now this is the PV diagram of an Otto cycle. Okay, now initially it is in state 0. State 0 means what? All these things are going to be in same line. Okay, this is the stage 0. This is the stage 0, and this thing is represented in PV diagram by this point. Okay, now this thing is 0. That means what? That means whatever, when the state is here, the volume is going to be up to here. Okay, the volume is going to be up to here. What is this volume at stage 0? What is the volume inside the cylinder? The volume is nothing but Vc. Okay, so up to this part, this is going to be Vc. Okay, in the cylinder, initially at stage 0, there is some volume of air. That volume is represented by 0.0, which is going to be about this much of volume. Okay, now this point is known as clearance volume. Okay, now after that, what happens while going to state 1? Okay, so from 0 to 1, what happens? There is a suction inside the cylinder. So while the suction is happening, what is going to be there? While the suction is there, this inlet valve opens. Okay, this inlet valve has come down. This inlet valve opens, and the air fuel mixture comes into the cylinder. So previously we have denoted the only air as blue dots. Now, to make you understand that there are some extra income of some air fuel ratio, we have denoted some of the dots with red dots. Okay, so that means what? This air is getting mixed with the air which is coming from outside. Okay, that is the air fuel mixture which is coming from outside. total mixture becomes like this, blue and red dot. Okay, now while the suction happens, the volume inside the cylinder is going to be what? The total volume of the cylinder. Okay, that means the point 1. This is the point 1. Okay, from 0 to 1 it is going to be a suction stroke. Okay, now for that suction stroke your volume comes from 0, from clearance volume to volume 1. Okay, this is the volume which is getting increased after point 0 to point 1. Okay, now what is going to be this volume? Previously the volume was, whatever the volume in cylinder there was, this was named as clearance volume. So this was the volume. After that, for reaching point 1, it has crossed the total volume. That means this is going to be the Vc and this is going to be the Vs. Okay, so what is the volume now inside the cylinder? That means at state 1, what is going to be the volume? The volume is going to be Vc, or clearance volume plus swept volume. Okay, so while you represent this, this total volume is, going to be Vs. Okay, this is due to the result of the suction. Okay, at suction stroke the piston is going to move total volume of swept volume, and whatever the air fuel mixture is coming into the cylinder is going to occupy the complete volume inside the cylinder. Okay, so from 0 to 1 the increasing volume is going to be equal to the swept volume. Previously it was clearance volume, then the increase was up to Vs, okay, or swept volume. Similarly here, previously it was Vc, now increasing volume is your swept volume. Okay, now from point 1 to point 2. Okay, point 1 to point 2, what happens? This is nothing but an adiabatic compression. Okay, this is nothing but an adiabatic compression. Adiabatic compression means what? Without the exchange of any heat, the air is being compressed. Okay, the air is being compressed. So this is the second state. This is the second state. This is the second state. In second state, what happens? The air, the piston goes up. Okay, the piston goes up. That means it is trying to compress whatever the gas it is having inside the cylinder. Okay, so it is compressing whatever the gases inside the cylinder to a small volume, which is again going to be Vc. Okay, that means now the mass of air is going to increase. Here whatever the mass is there, the mass is going to continuously increase here, because there are some air fuel mixture from outside also. So mass is going to increase here. Now the same amount of mass is compressed. So whatever the mass of air was here although the volume is same, the mass is going to increase because there are some air fuel mixture also. So again the piston is trying to compress this total mixture. Okay, it is trying to compress this total mixture, and compress to what volume? Compress to up to what extent the piston can go. Okay, so the piston can go up to Vc. Okay, the piston can go up to Vc, or clearance volume. That means what? The piston is trying to compress this air fuel mixture into a volume called Vc. Okay, or this is the volume. So this is point 1. From here it is trying to compress the volume. Okay, again up to Vc. Whatever the point it was in 0, it will be linear, because all the dots, okay, or the point 3, point 2 and point 0 are going to be linear here, and they are all going to be in same line, which will coincide with our Vc. Okay, which will coincide with our Vc. So the piston has compressed the air fuel mixture up to Vc, okay, or clearance volume. Now in the third point, okay, while moving from 2 to 3, what is going to happen? While moving from 2 to 3, it is nothing but an constant volume heat addition. Okay, so keeping the volume constant, we are going to add heat. How we are going to add heat? Okay, so this is an Otto cycle or petrol engine. And petrol engine, what is going to be there? There is going to be spark ignition. Okay, in petrol engine there is always spark ignition. Spark ignition means while the air fuel mixture is compressed, okay, here air fuel mixture is going to get compressed. Okay, so while compressing, what will happen? While compressing, the volume is also decreasing. Okay, and from point 1 there is a pressure, and point 2 there is also a pressure. So while compression, while compression is going on, there is some increase in pressure also. Okay, so here some pressure is also going to be there. Okay, and the compression is also going to be there. In the third state, this is a spark plug. Okay, this is a spark plug. Okay, so now whatever the air fuel mixture has been compressed here are in high temperature. Okay, are in high temperature or on the verge of ignition. Okay, on the verge of ignition. Now it just requires a little flame so that it can burn. Okay, it just requires a little flame so that it can burn, because this temperature pressure is all very high. After compression, is temperature and pressure is going to be very high. So we provide some spark through the spark plug. Okay, through the spark plug we are going to provide some spark. Okay, so with that spark, what is going to happen? The total air fuel mixture, which is very compressed and going to have a very high temperature, is going to burn. Okay, so this total complete thing is going to be from 2 to 3. Okay, that means up to 0.3 the volume is going to be same. Okay, and the combustion of these particles inside the cylinder is going to burn. Okay, now from 3 to 4 what happens? From 3 to 4 what is going to be there? So after burning, what will happen? This temperature of these particles is going to be more again. Okay, it will be so high, that it will try to expand. Okay, it will try to expand. So with the high temperature and high pressure, what is it going to be? It is going to expand. Okay, because it has been burned, the temperature is going to be high, so it is going to expand. I am showing these particles in terms of black dots because we are going to make you understand that these particles have now burned. So after burning, the particles has become black. Okay, so from 3 to 4, okay, from 3 to 4 what is going to be there? There is going to be an adiabatic expansion. Okay, this is an adiabatic expansion. Adiabatic expansion is what? When the expansion is taking place, no heat exchange with the surrounding is going to take place. Okay, so from 3 to 4 what is going to happen? From 3 to 4 the piston is again going to expand. And what is the total volume of the cylinder now? It is the total volume, clearance volume plus swept volume. So you can see it here, the 0.4 which is represented in PV diagram. If you project it on volume axis, then you will see that the 0.4 is having a volume of clearance volume plus swept volume. Okay, now this is up to 0.4. Now 4 to 1, this is again 0.1. Okay, previously this was 0.1 and there was some air fuel mixture. Okay, now there is some burned particles. Okay, or after combustion, whatever the products are there, it is going to be in 0.1. So while from 4 to 0.1 nothing happens, only the volume is constant. Keeping the volume constant, the heat is going to get released. Okay, heat is going, that is from this through the path 4 to 1. Through the path 4 to 1, the heat is going to get released. Okay, so that means keeping the volume constant, only the heat is going to get released. So while the heat is going to get released, what is going to be there? Whatever the pressure was inside the cylinder, that pressure is going to come down. Okay, so you can see here what is the pressure here. Suppose this is 0.4, is going to have a pressure of P4. Okay, so while the heat is going out, keeping the volume constant, the pressure inside the cylinder is going to come down to P1. Okay, or pressure at P1. Okay, so while this is 0.1, what is going to happen? From 0.1 it will again go to 0.0. That means the piston will go up. And the valve, okay, whatever the valve is there, the exit valve is there, the pressure inside this, okay, is going to help us move this valve. Okay, move this exhaust valve, and whatever the exhaust particles are there, they are going to go out through this exhaust valve. Okay, so what are the basic processes? What is going to happen here? First of all, there is going to be a cylinder, okay, and having a clearance volume with some of the air particles. In the second part, the piston is going to come down. Some of the air fuel mixture is going to come inside the cylinder. In the second portion, what is going to happen? Again, the air fuel mixture which has come into the cylinder is going to get compressed by the piston, Okay, and in this point whatever the spark is provided and the compressed air fuel mixture is going to now burn. So after burning the piston is going to expand. Okay, and the total volume is total volume of the cylinder will be in action now. Now after that point 1, in point 1 what happens, this is the point after releasing the heat, the pressure is going to come down. Okay, and from point 1 it is again going to point 0. Okay, in point 0 what is going to be there, from 1 to point 0 whatever the particles are inside the cylinder, it is going to go out through the exhaust valve. Okay, but after completion, after going to 0, okay, this point will come, but previously there were some blue dots. Now after compression there will be some black dots. Okay, that means what, in only the first cycle, initially pure air is there. Okay, initially pure air is there, but while the second cycle starts, okay, now this is going to point 1 means point 0, this from point 1 it is going back to point 0. That means what, the piston is going up, but the particles are now going to be represented by black dots. That means whatever the particle that would be remaining will be some products of the combustion. Okay, so only in while the first cycle starts, then only there is going to be some pure air. Okay, while starting the second, third and consecutively whatever cycles you start, in those cycles the initial particles are going to be your product of combustion. Okay, so the efficiency decreases only in the first cycle, the efficiency is going to be there, but after that efficiency is going to decrease, but it is very negligible. Okay, because previously there is some exhaust will be present from the second cycle. Okay, so this is the Otto cycle represented in PV diagrams, and its corresponding point as a cylinder are shown here. Okay, so this is our Otto cycle. Okay, so now we are going to see some of the terms related to Otto cycle. Okay, and these terms will be very important for us while finding the efficiency of an Otto cycle. Okay, so the first term we are going to learn is compression ratio. Okay, now compression ratio is what? Compression ratio is nothing but the volume before compression and volume after compression. Okay, that means it is the ratio of volume before compression to volume after compression. Now if you see the PV diagram, in PV diagram process 1 to 2 was a compression stroke. Okay, and 3 to 4 was the expansion stroke. Okay, now if you see the compression stroke, in this compression stroke the compression is going to happen inside the cylinder. Okay, that means from this point 1, okay, or the volume at point 1, the volume at point 1 is going to be named as V1. Okay, and this V1 is what? The V1 is volume before compression. Okay, the volume has to happen after it gets to point 1. Compression has to happen after it gets to point 1. Okay, so before the compression whatever the volume this is having is going to be equal to V1. Compression ratio is represented by R, so volume before the compression is V1. Okay, or whatever the volume at point 1, and volume after the compression is what? Is going to V2. That means after the compression it is reaching the point 2. Okay, so whatever the volume is going to be there is going to be our V2. Okay, now if you remember what is going to be V2, okay, V2 is what? After the compression what was the volume of the air inside the cylinder. Okay, so in the diagrams we have seen that whatever the V2 was there, it has been compressed to the clearance volume only. Okay, the total volume has been compressed to a volume of clearance volume. Okay, so this is going to, V2 is going to represent the clearance volume, and V1 is what? If you measure it from origin, that the total length is going to be your V1. Okay, so now you can see up to V2 it was VC. Okay, or the total volume has been compressed to clearance volume, and the increase of the volume while suction was there, the increase of the volume or the swept volume, that means how much amount of volume the piston has to cover so that the total volume of the cylinder is going to get compressed into a clearance volume, it is the swept volume. Okay, the piston has to travel the swept volume so that the air fuel mixture inside it goes to clearance volume. Okay, or reaches to clearance volume. So from the diagram you can see that we can write V1 is equals to VC plus VS. Okay, or V1 volume at 1 or the complete volume of the cylinder is going to be what? Is going to be equal to clearance volume plus swept volume. Swept volume. Okay. So in place of V1 you can write Vc plus Vs. Okay, you can write Vc plus Vs, and V2 is what? V2 is nothing but the clearance volume. Okay, this is going to be your clearance volume. Okay, now this is R, this is known as compression ratio. This is going to play a major role in our efficiency. Okay, now for SI engine is what? Spark ignition. Okay, spark ignition is what? Spark ignition engine is an engine where we initiate the ignition, okay, or initiate the combustion of the air fuel mixture which has been compressed inside the cylinder, okay, with the help of flame. Okay, that's why in Otto cycle I have shown you that we are using some spark. Okay, by using the spark, what we are doing, we are initiating the ignition of the air fuel mixture which is going to be, or which has been compressed inside the cylinder. Okay, so these are known as spark ignition engine. So the R here is going to be 8 to 12. Okay, and this is compression ignition engine. Compression ignition engine is what? It is such type of an engine, okay, such type of an engine where we compress the air fuel mixture so high, okay, or in a so high ratio or so high compression ratio, such that that means we are compressing it so high that the pressure inside it is increasing and the temperature is also increasing, and finally the temperature reaches its self ignition temperature, and once the self ignition temperature is reached for the fuel, it burns automatically, okay, or it ignites itself. Okay, so in compression ignition engine the ratio is going to be 16 to 24. Now it is going to be so much higher than this, so much higher than the spark ignition engine in comparison to the spark ignition engine. Why? In spark ignition engine we have something to initiate the ignition, whereas in compression ignition engine we have nothing to initiate the ignition. We have to attain the temperature, or we have to attain the self ignition temperature of the air fuel mixture by compressing it only. Okay, by compressing it only we need to initiate the ignition. Okay, so that's why, since we don't have any initiation or helping hand for starting the ignition, we need to compress the air fuel mixture inside a compression ignition engine very much higher. So that is the reason why we are having the compression ratio for compression ignition engine very high. Okay, that means what? The initial volume, okay, the initial volume of the air is going to be constant. Okay, you are not going to expand it. If you are going to expand that initial volume, it is going to be nothing but a negative work. Okay, it is going to be nothing but a loss of work. Okay, because if you increase the volume, this is going to be your initial volume. Okay, so to increase the compression ratio, what you are going to do, either you are going to increase this or you are going to decrease this. Okay, either you are going to increase this and this is, or you are going to decrease this. Now increasing this would be negative work. Okay, only a waste of time. Increasing this is going to be a waste of time. Why? Because your final condition is reaching here. Your final goal is to reach at point 2. After compression you need to go to point 2. Now if you increase volume 1 and after that you decrease volume 2, is it going to be helpful? Your final result is not going to be final compression in the final compression, okay, or the final volume which you are going to attain after the compression is not going to be helpful, because if you increase it again you are decreasing it to 0.2. okay, then what it is going to be there, it is nothing but the waste of time while you are coming up to this increased volume, and while going back to up to 0.1 is going to be total waste of time, because after reaching volume 2, whatever the temperature it has to attain is going to be same if your 0.2 is same. Okay, if your 0.2 is same, then whatever the temperature or pressure it has to attain while compressing it from 0.1, okay, or in the case of increasing the 0.1 and then decreasing again, whatever the temperature it has to develop, it will be same only. Okay, that means to increase your compression ratio, okay, or to develop your compression ratio, you need to you need to decrease the volume 2, keeping the volume 1. This is the initial air fuel mixture. Okay, it is the natural air fuel mixture volume which it is coming. Okay, now you need to decrease the volume 2. Decrease the volume 2 so that you can compress it more and more. Okay, the volume after compression becomes smaller and smaller and the temperature rises. Okay, so to increase the compression ratio, we need to decrease the volume 2. Okay, so this was our compression ratio. Next thing is our expansion ratio. Expansion ratio is what? Expansion ratio is nothing but volume after expansion and volume before expansion. Okay, now you can see here in compression ratio it was volume before compression in the top. Okay, now here volume after expansion is going to be in the top. Okay, we are keeping this in such way so that the compression ratio and expansion ratio becomes greater than 1. Okay, here volume 1 is going to be higher than volume 2, so it is always greater than 1. Okay, similarly expansion ratio is also going to be 1 because volume after expansion is what? This is the expansion stroke. After expansion it is going to be V4. Okay, it is going to be V4, and volume before expansion is nothing but 3. Okay, this is the expansion stroke. So before the starting of the expansion, what is going to be the volume? The volume is V3. Okay, now if you see in the diagram, V3. Now if you see in the diagram, you will see that volume 3 and volume 2 are going to be same because the heat addition process was constant volume. Heat addition process was constant volume. Okay, so the volume at point 2 and volume at point 3 is going to be same. Okay, this is a constant volume line. This is also a constant volume line. So volume at point 4 is going to be same as that of volume at point 1. Okay, so in place of V4 you can write V1, and in place of V3 you can write V2. So this is going to be again equal to compression ratio only. Now all these things are only for Otto cycle. Okay, don't confuse it for the other cycles. These derivations which we are showing is only for Otto cycle. Okay, only for Otto cycle. Now again the things we need to know. Okay, what is going to be the heat addition to the process and what is going to be the heat rejected from the process. Okay, now there was point 0. While understanding the Otto cycle, we had represented a point 0 in that place. Okay, now we are removing that part. Okay, because the main cycle starts from point 1 only. Okay, after the point 0 to 1 has been attained, then the cycle is completely closed. Okay, then the cycle is completely stopped until it reaches here again. From 4 to 1 until it reaches here again, that complete process is going to be inside a closed system. Okay, so before reaching point 1, it is going to be an open because mass transfer is, air fuel mixture is coming in. So mass transfer is going to take place. Again from 4 to 1 while it is reaching, after that 1 it is again going to point 0. And in that process what is going to be there? The expansion, the exhaust is going to take place. Whatever the burned particles are there from the combustion or the combustion products are there, they are going to go out. That means again mass transfer is going to take place. So while reaching from 0 to 1, okay, so while reaching from 0 to 1 it is going to be an open cycle. But once the point 1 has been reached, this is going to act as a closed cycle and it is going to act as a cycle. Okay, until the point 1 is reached. Okay, now what is going to be the heat addition? I am saying this because I have once said that when there is a cycle, okay, when there is a cycle, then the area enclosed by the cycle, in a PV diagram is going to give you your total work. Okay, the area inside the cycle is going to give you your total work. Okay, now process 2 to 3. Okay, process 2 to 3. That means 2 to 3. What is going to be the heat addition? Again we know whatever the mass of air is there inside the cylinder, okay, the total mass has to be get heated, okay, or the total mass has to be get heated by this Q in, okay, or this is the amount of heat transfer. So M is what? M is the mass of air. This is the specific ratio. Since 2 to 3 is going to be a constant volume, so we are putting a, and this is an air standard cycle. Okay, so whatever, this is an air standard cycle. Okay, Otto cycle comes under air standard cycle. So the the substance which will be going substance that will be inside the cylinder is going to be air only, okay, pure air only. Okay, so we are taking CV value, CV for air, and what is going to be the temperature difference. Okay, we all know that heat addition is m into c into del T. Okay, now C, in case of gases, C is of two type, okay, CP and CV. Since it is constant volume, we are writing CV. So mass of the air into specific heat into del T. Okay, for process 2 to 3, whatever the temperature it has attained in point 3 and whatever the temperature it was before the heat addition, the difference will give you the heat addition. Okay, that means the final, what is the amount of heat added, the Q in is going to be m into CV into T3 minus T2. Similarly, for process 4 to 1, it is again going to be a constant volume, so mass of air inside the cycle is going to be same only, so m into CV. Since the air is going to be same, okay, that means the CV and CP are constant values. Okay, so whatever the air, whatever the substance is inside the cylinder, okay, for that the CP or CV value is not going to change. Okay, the only thing that will be different is whatever the temperature difference it has been or whatever the temperature difference has been observed while reaching from point 4 to 1. Okay, so we'll subtract T1, okay, that is the final temperature. Since it is rejecting heat, the final temperature is going to be lower than the initial temperature. Okay, so we are going to take the difference of T4 minus T1. Okay. Okay, so now we are going to see what is going to be the efficiency of an Otto cycle. Okay, now we know that whatever the cycle it is, the efficiency is nothing but whatever the output we are getting divided by whatever the input we are going to give. Okay, now it is efficiency of Otto cycle, eta Otto is there. Okay, now it is the ratio of W net. Okay, whatever the net work we are going to get divided by the energy input we are going to give. Now in Otto cycle we are going to give the energy in terms of heat. Okay, that is Q in. So this is going to be the Q in which we are going to give. Okay, now if you remember the first law of thermodynamics for a cycle. Now first law of thermodynamics was written for two things. Okay, one for process and one for cycle. The process is not needed here because this is Otto cycle. Okay, this complete process is going to act in a cycle. Okay, so we are going to apply the first law of thermodynamics for a cycle. Now what was the first law for cycle? It was the net heat interaction is going to be equal to the net work interaction. Okay, now in this cycle what are the heat interactions? We are going to give heat and some of the heat is going to get rejected. Okay, so the net heat interaction is going to be what? The Q in, we are going to give heat to the system. Now giving heat to a system is always positive, so Q in is going to get positive. And Q out, that is some of the heat is going to get out from the system. Okay, that means what? We are going to put negative sign here, and this is the W net. Okay, the net work transfer we are going to get is going to be W net. Okay, so we know that W net is what? The total heat input minus the heat output is going to give you your W net. Okay, now we are in this formula we are going to replace W net with Q in minus Q out. Okay, so Q in minus Q out and divided by Q in. Now if you simplify this, you are going to get 1 minus Q out by Q in. Okay, now in place of Q out, we are going to put the expression which we got earlier. Okay, so this was the expression which we got earlier, m into Cv into T4 minus T1. So this I have written here. Okay, next thing is Q in. In place of Q in, we are going to write down the expression which we have got, that is m into Cv into T3 minus T2. Now here will get cancelled. Why is going to get cancelled? Because as I have told earlier, it starts from 0. Okay, we had put a point here 0. Okay, now we have said that it comes from 0 to 1. Okay, now after coming to 1, it goes to 2, 3, 4 and then again comes back to 1. Okay, now during this cycle, during traveling from 1, 2, 3, 4 and 1, the valves does not open. Okay, the valves does not open. The valve will open only when it is coming from 0 to 1, and again the exhaust valve will open when it is going from 1 to 0. In between this, the inlet or exit valve does not open. Okay, it does not open means what? There is no mass transfer. Since there is no mass transfer from 1 to again coming back to 1, there is no mass transfer. That means this is going to be a closed system. Okay, a closed system, and it is going to be run on a cycle. Okay, now as this is closed system and there is no mass interaction because the valves does not open, that means what? the mass inside that thing is going to be constant. The volume will continuously go up and down, but whatever the mass or the mass of that air fuel mixture which we had taken out in the first stroke, okay, from 0 to 1, that mass is going to be constantly there in the cylinder until and unless it is coming to point 1 and leaves it through exit valve. Okay, so before that the mass is going to be constant, and this is an air standard cycle. That means the substance inside the cylinder is going to be nothing but air. Okay, and this is air. That means whether its density changes or not, the specific heat at constant volume or specific heat at constant pressure, these are the constant values. This does not change. Okay, now since the substance is air, that means CV value is also going to be same for in and out. So M and CV is going to get cancelled. Okay, now the remaining thing is 1 minus T4 minus T1 by T3 minus T2. Okay, now from this thing you are going to take T1 common. Okay, if you take T1 common, the remaining thing is T4 by T1 minus 1, and from the denominator you are going to take T2 common. If you take T2 common, you are going to get T3 by T2 minus 1. Okay, now in the chapter of specific heat, or in the second chapter, you will find that we have derived these things. Okay, for adiabatic process, when there is gamma, you need to understand that this process must be for adiabatic process. Okay, if gamma is there, that means for adiabatic process. Now you will find that if you check your notes, you are going to find that I have said for adiabatic process, for an adiabatic process, so I have written from 1 to 2. 1 to 2 is what? It is a compression is going to take place, which is adiabatic. Adiabatic compression is going to take place here. So for adiabatic process, we have found that the final temperature by initial temperature is going to be equal to initial volume by final volume to the power gamma minus 1. Okay, and V1 by V2, if you remember, we have found out that V1 by V2 is going to be nothing but the compression ratio. Okay, so in place of V1 by V2, I have written compression ratio R to the power gamma minus 1. Okay, similarly 3 to 4. 3 to 4 is an expansion stroke, but this is also an adiabatic process. Okay, now since it is adiabatic process, that means what? Adiabatic process, that means this relation is again going to be valid. Okay, that means T3 by T4 is going to be equal to V4 by V3 to the power gamma minus 1. So these are the formulas you need to recapitulate before you start this chapter. Okay, so you will find in your notes that these are going to be the conditions. Okay, again V4 and V1 are same, V4 and V1 are same, V3 and V2 are also same. So we have found out that this ratio and this ratio are both equal to compression ratio. So in place of this, we are again going to write R equals to gamma minus R to the power gamma minus 1. Okay, now you see this term and this term is going to be same. This is also a compression ratio to the power gamma minus 1. This is also compression ratio to the power gamma minus 1. Now since both of these are going to be same, that means these terms are also going to be same. Okay, so I have written down here. Okay, this equal to this. Now from this we are going to get that T4 by T1 and T3 by T2 are also going to be same. Okay, T4 by T1 and T3 by T2 are also going to be same. Now here T4 by T1 is there, T3 by T2 is also going to be there. Okay, T4 by T1 equals to T3 by T2. That's why these two things are also going to get cancelled. Okay, now the remaining thing is what? 1 minus T1 by T2. Okay, 1 minus T1 by T2. Now from here you are going to see that T2 by T1 is equal to what? R to the power gamma minus 1. This is T2 by T1. Here it is T1 by T2. So in place of this we can write 1 minus 1 by R to the power gamma minus 1. Okay, since it is T2 by T1, it is direct R to the power gamma minus 1. Now it is T1 by T2. So we are doing writing the reciprocal of this one. Okay, this is the reciprocal of this one. So this will be the reciprocal of this one. Okay, so this is the final formula of Otto cycle efficiency. Okay, if the compression ratio is given directly, you can directly find out what is going to be the efficiency of an Otto cycle. Okay, if nothing is given, if heat interaction or work output are given, then you can easily find it by any of the, okay, in between any of the line is there. You just need to pick your formula according to the data they have given. Okay, according to the data they have given, you need to find what formula you need. Okay, if work interaction is given, heat input is given, you can directly find efficiency from here. If heat input is given, heat rejected is given, then you can find efficiency from here or here. Okay, if all these data are given, then you can find it from here. If the temperatures are given, T1 and T2 are given, okay, if T1 and T2 are given, then you can also find efficiency from here. Okay, but ultimately this is very important, this formula is very important, okay, according to gate point of view. So I have made a boundary in this so that it could be remembered. Okay, this formula is going to be very important in terms of gate. Okay, and the remaining things are very basic, okay, you can easily remember these things. Okay, but this one is very important. Okay.